Hello everyone, welcome to Physics Mage. This is a good problem to understand the concepts of mutual inductance, electromagnetic induction, Lorentz magnetic force, and few approximations. Let's try and solve this problem. In the figure shown, two loops ABCD and EFGH are in the same plane. So these are the two loops here they have given already. So ABCD is carrying current like this and EFGH in the same plane such that the smaller loop carries time varying current I is equal to Bt, where B is a positive constant, T is a time. The resistance of the smaller loop is smaller and that of a larger loop is capital R. Neglect the self-inductance of the larger loop. The magnetic force on the loop EFGH due to the loop ABCD is. So they have given an expression here and we are asked to find the value of this X here. So dear students, to try and solve this problem, we need to know a little bit of basic concepts. So I will just list out the concepts which we'll be using. See, you should know, like, suppose if we consider a infinitely long wire carrying current, meaning pretty long wire carrying current, okay, it is very large value of length, then the magnetic field at a point because of this particular wire carrying current is given by mu naught I divided by 2 pi r if I is a current flowing through this. This you should know. Suppose if you are interested in calculating flux through any particular region, let's say if we know that magnetic field here is passing through this particular region, and if you want to know like flux through this particular area, we can write like phi is equal to integration of B dotted with dA, where dA is the small area we are selecting here. Okay, like this, and we will integrate this to get the total flux through this particular area. And of course, if magnetic field is same, we will have phi is equal to B dotted with A. And I hope you're all familiar with this ideas. Okay. Then also I would expect you to know mutual inductance of the first coil in relation with second coil will be equal to mutual inductance of the second coil in relation with the first coil. Okay. So this is also an important idea. Then we have Faraday's law of electromagnetic induction is minus of dou d phi by dt. This is magnetic flux total that can also be written as minus of m into di by dt. Whenever we write m is mutual inductance and I is the current variation happening in the neighboring coil. Okay, so it's like if you have two coils, like say coil 1 and coil 2. Suppose if you know like current is changing the first coil, and if you're predicting EMF induced in the second coil, okay, then you'll be using this particular relation. And we also should know like the force experienced by the current carrying wire placed in external magnetic field is given by ideal cross B on an element, current element. And to get the total force, we will be integrating this. Usually we will write like BIL if or else we can write it as I times of L cross P if magnetic field over length is same. Okay, so I hope these are the basic concepts one should know before solving this problem. Now the plan to solve this particular problem is, say we are considering here there is a flow of current and this current I is changing with time. As this particular current is changing with time, the magnetic field produced by this coil will be into the screen here, the magnetic field produced by this coil, and that particular field here through this particular coil, it will be coming outside. So I hope you know these ideas. So you can imagine this one as a current carrying coil producing a magnetic field. It is acting like a source of magnetism, and that will be creating the field around it. So magnetic field here in this EFGH coil will be outwards. And since here current is changing with time, obviously magnetic field will keep changing. As current is increasing, this magnetic field will also increase. And according to Lenz's law, you know that, dear students, here you should know a little bit of other concepts also, like Lenz's law and V is equal to I times of R and Newton's third law, action reaction. These are like basic concepts you should be knowing. So here this magnetic field is increasing, right? So according to Lenz's law, we know that this EFGH coil should circulate the current in order to counter this increasing magnetic field. So obviously it will circulate current in this manner in order to counter the increasing magnetic field, correct? So let me say the current flowing through this secondary coil, right? Or EFGH coil, that I'll be naming it as I dash, okay? I dash is the current flowing through the secondary coil. Force exerted by this EFGH on ABCD coil. Okay, so if we know force exerted by EFGH on ABCD coil, then from Newton's third law, we can say that ABCD is experiencing force because of EFGH, then obviously the equal force will be exerted by ABCD on EFGH, and that is our question. So that's our approach. The magnetic field produced at the site of ABCD because of the current flowing through EFGH coil. See, we know that I'm just representing I dash as the symbol, right? So we are just considering some position, okay, at which, suppose if I take this is some random position point P, which is at a distance x from the like EH conductor. What is the magnetic field at this point because of this EH conductor carrying current? So that magnetic field is given by mu naught times I dash divided by 2 pi times of x amount of distance. Okay. Now we know that here the current is flowing upwards. So the magnetic field at this side because of this current carrying wire, right? That would be obviously upwards. This is the magnetic field B dash because of this EH current carrying wire. Okay. So I'll be just writing like this just for symbolic representation. B dash. B dash is different from the magnetic field produced by ABCD coil itself. Okay. Now this is B dash mu naught I dash by 2 pi x, and also even F and G will also produce, and that will be into the screen, right? So if EH will be out of the screen and FG will be into the screen, and I hope you are familiar with how magnetic field lines will be because of a current carrying wire. So I'll be writing minus of mu naught times of I dash divided by 2 pi times of x plus a. So we know that if we consider the magnitude, this is it. Suppose if you want to write in terms of, vector format, we'll be writing mu naught I dash divided by 2 pi times 1 by x minus of 1 by x plus a. The direction is outwards. This is the magnitude and the direction is outwards. Okay. I'll be writing outwards just for our understanding. Okay. Now, once we get this idea, what next? Now, we'll be selecting a small portion here to calculate the flux. In order to calculate the flux, I'll be selecting a small region here. And this region, let me call it as dA region. Okay. So dA dotted with magnetic field B dash, that will be the small flux through that particular region. Suppose if I want total flux, I'll be integrating this. And you know that here B dash and dA can be taken in the same direction, so that our small flux becomes like whatever the like total flux we can calculate. The total flux will be equal to integration of B dash dot dA, and we have to select this particular dA value so that we can easily integrate. So we have B dash value as mu naught I dash by 2 pi times 1 by x minus of 1 by x plus a, and dotted with dA. dA is here the length of this particular red color shaded portion, right? That would be A, and the thickness is dx. I'll be choosing the thickness value here, the thickness, right? This portion, the thickness value as dx. Dx is the thickness of the strip. Okay. So using that here, A times of dx is a small area and cos of 0 degrees because I'm assuming area dA as well as B dash in the same direction. Okay. So using that information, we'll get flux equals we have to integrate this, and our variable here is x, and x varies from A to 2A, right? A to 2A. That's how it varies. And see here I'm considering the magnetic field contribution at this point, some point P we are recognizing, right? At the point P, at some point P, the magnetic field is given by this. You might be wondering what about like the EF conductor here as well as GH conductor? Will they offer magnetic field or not? They will definitely offer, but according to this approximation, L is much greater than A, right? So you can imagine that A is really small, and the contribution from EF conductor and HG conductor is really small, so we are ignoring that. Meaning magnetic field will be there, but even if you consider, there won't be much of a difference. Okay, meaning we are neglecting its contribution. That's one of the approximation we are using. Okay, now after using this approximation, we can say here mu naught I dash by 2 pi, and here integration here. So ln of x minus of ln of x plus a. I'm just integrating with respect to x, and I have a here. I'm supposed to write a here, right? So this is what our integration is, and our integration limits from a to 2a. So if we simplify this, mu naught I dash a by 2 pi and ln of, I'll be first rearranging these terms, x by x plus a, and the upper limit and lower limit as 2a upper limit, lower limit is a. So which implies the flux value would be mu naught I dash a divided by 2 pi times of ln of 2a divided by 3a minus ln of a divided by 2a. So the flux is going to be mu naught I dash a divided by 2 pi times, say we can write this one as ln of 2a by 3a and a by 2a, right? You can simplify this and it turns out to be ln of 2a by 3a and a here and 2a here, right? So we can simplify this and write it as, we can directly write this one as 4 by 3. So phi becomes, I'll be highlighting this idea here. So phi becomes mu naught a divided by 2 pi times ln of 4 by 3 times of I dash. This is our first equation. This is our first equation. Let's say this is our second equation. Okay. Now using our second equation, we can say that using our second equation, that flux will be equal to mutual inductance times the current in the neighboring coil, right? Suppose say this is a flux in the first coil, which is ABCD coil, and that is happening because of the current variation happening in the second coil. I dash is the current in the secondary coil, right? EFGH. So we can say that mutual inductance of the first coil in relation with the second coil. Mutual inductance of the first coil in relation with second coil, we got already now. This is using equation 2. Using 2, we have mu naught A by 2 pi, mu naught A by 2 pi times of ln of 4 by 3, ln of 4 divided by 3. This is what we have for mutual inductance. Okay. Now once we are done with mutual inductance, what next? Now we will think of Faraday's law. So Faraday's law gives information that the induced EMF in the secondary coil, which is this EFGH coil, the induced EMF in the EFGH coil, that we can think as equal to m times of mutual inductance of first coil in relation with second coil is equal to mutual inductance of second coil with respect to first coil, right? This we know from reciprocity theorem. So we can say induced EMF is equal to m21 times di by dt. See here, I is the current in the first coil. Okay, so if you want to stick to the same notation which we had before, you can write it as di by dt, because here I is the capital I is the current flow in the first coil. Okay, and this is induced EMF in the second coil. Okay, and we know that here epsilon 2 equals M21 we already got it. So M12 is equal to M21, right? So it is mu naught A divided by 2 pi times ln of 4 by 3 and d by dt of this A. And what is the value of this A? Sorry, value of I. Value of I is equal to B times T, right? So I'll be writing here B times T, and we'll have induced EMF in the second coil is mu naught A by 2 pi times ln of 4 by 3. This is just in differentiation of Vt is just B. So I'll be writing here. So this is our induced EMF in the second coil. Then the current produced in the second coil times the resistance of the second coil gives us induced EMF in the second coil. That would be equal to mu naught AB times ln of 4 by 3 divided by 2 pi. So basically we got current in the second coil, which is mu naught AB divided by 2 pi capital R times ln of 4 by 3. Ln of 4 by 3. Dear students, here they have given the value of resistance of the second coil, big coil, EFGH, right? That is capital R. Okay. So knowing all these things, what next? Once we know the current flowing in the second coil, our plan is this. Since we know that there is a small coil here and a bigger coil, okay. Now, since we know that current is flowing in this particular coil, the value of it, we got it here, okay. Now we will plan for what is the force experienced by this ABCD coil because of this EFGH coil. So that's our plan. Now, anyhow, we got this idea, right? The magnetic field at this point would be upwards. This B dash would be upwards because of this particular EH current carrying wire as well as FG current carrying wire. So our plan is, if you think of AB alone current carrying wire, and we know that current flowing in this particular coil is clockwise like this, clockwise, and in this particular fashion it is moving. Now, if AB, if you consider ideal cross B, force experienced is given by ideal cross B, right? It's a force experience, small force experienced on a current element. If I choose a small current element here on this one, ideal cross B gives me the force. Ideal cross B gives me the force in this direction, and here ideal cross B gives the force in this direction. So basically these two will cancel each other. So I'm considering the magnetic field produced by EH, right? EH, that will be out of the screen. So the current element chosen on AB and CD will cancel each other. So basically we don't have to worry about the AB segment and CD segment. Okay. Now we are finding out the force on ABCD coil. Force on ABCD coil. On the ABCD coil. For finding force on the ABCD coil, first I will recognize the magnetic field at this first site, no, first site and second site. First site is magnetic field at the first site dash, it is equal to mu naught times I dash divided by 2 pi A, because A is the distance from the first wire to this first site. Okay. And because of the second fellow, we can find out the magnetic field at that point. It is minus of mu naught I dash divided by 2 pi times the overall distance would be, this is A, and even this particular distance from G to H also A. So it turns out to be 2A, right? So 2A like that. This is a magnetic field at the first site. So mu naught I dash divided by 2 pi A times 1 minus 1 by 2. That's what we have. So B1 dash is going to be mu naught I dash divided by 2 pi A times of 1 by 2. So basically it is 4 pi A. Okay. So same thing we will plan for at the second site also. Okay. At the second site it is B2 dash, which is going to be mu naught I dash divided by, see, from EH site to the AD segment, right? The overall distance turns out to be 2a, right? Okay, so it is going to be mu naught 2 pi times of 2a minus of mu naught I dash divided by 2 pi times of 3a. So this is because of FG segment. Okay, and again I'm repeating EF current carrying wire and HG current carrying wire will produce magnetic field, but since we are ignoring the contribution from that, we are not writing it. Okay, so using those things we can write B2 dash would be mu naught I dash divided by 2 pi a times 1 by 2 here minus 1 by 3, right? So it's going to be mu naught I dash by pi a. This is going to be 1 by 6, right? So basically 1 by 12 pi a. So please observe, this is what we have. Now once we know that this is b2 dash, b1 dash is already we found the value of b1 dash. b1 dash is mu naught I dash by 4 pi a, mu naught I dash divided by 4 pi a. Say I'll be writing mu naught I dash by 4 pi a as 12 pi a into 3. I'm just multiplying and dividing by 3. That's it. So we can say now the force exerted, force on the coil ABCD is going to be F equals I is the current flowing through that particular coil, right? So the current symbol we are using capital I, and the length of that particular small coil is A, and B1 dash minus of B2 dash. Okay, now we know that B1 dash and B2 dash, right? B1 dash is the magnetic field exactly the first site. So I'll be highlighting that here. See, B1 dash would be here outwards like this. This is what we are calling as B1 dash. Here B2 dash, B2 dash, even that is outwards. So current flowing through BC, right? That will experience force, ideal cross B, right? It will experience force towards this side, ideal cross B. In this direction, I have shown in the green color vector. Here, ideal cross B. Here, it is going to be like this, ideal cross B, the opposite direction for AD segment. Since BC is closer to the wires than AD, right? So BC force will be larger. So I'll be calling this one as F1 and this is F2. Okay. So F1 will be leftwards, F2 will be rightwards, F1 will be stronger. Okay. F1 will be stronger. The net force is given by BIA B1 dash minus B2 dash, right? So this is F1 minus F2, and this force is basically towards leftwards. Okay, and force will be equal to I times A B1 minus B1 dash minus B2 dash. B1 dash minus B2 dash, here we can use these values and write it is 2 times of mu naught I dash divided by 12 by A. We can further simplify this. I times of A, this is mu naught I dash by 6 pi a, right? So 2, 6, okay. I suppose to write the value of I dash here. So I dash value we already have here. We found this value of I dash here. We can call this as equation number 3. So if you call this as equation 3, using 3. Using 3, we can write the value of I dash as mu naught AB by 2 pi r, mu naught AB by 2 pi r times ln of 4 by 3. Ln of 4 by 3. This is what we have. So then the force can be written as mu naught times mu naught. It is mu naught squared, a squared. One of the a getting cancelled out, let's say. So just AB, mu naught squared AB times of I divided by, in the denominator we have 6 times 12 pi squared times of r and a ln of 4 by 3. This is a force on ABCD, right? Force on ABCD due to EFGH. If this is the case, then according to Newton's third law, for this force, there should be reaction pair also, right? So now we will compare this particular relation with whatever is given in the question. So we have mu naught square AB times of I divided by 12 pi squared r ln of 4 by 3, right? So our so-called x value is going to be 12. So this is the solution for this given problem. So I hope you understood this particular solution and approach. And if you have any doubts, please comment that in the comment section. Thank you, everyone.